Hello, I'm Chris Hay, Extension Water Management Engineer from the Department of Ag and Biosystems Engineering at South Dakota State University, and I'll be guiding you through this distance learning module on basic drainage concepts, tools, and resources. To start with, here's my contact information, so if there are questions that develop as we go through this, please feel free to contact me and I'll be happy to try and answer those. And then just a reminder that this module is one of 8 distance education modules, all designed to prepare you for the on-site training sessions as part of the Drainage Water Management Level 2 training. What I intend to cover in this module then is, first of all, some basic soils and drainage concepts, some basic concepts of drainage design, and then some design tools and resources that are all available to help assist you with drainage design. Diving right into the basics of soils and drainage concepts, what we're talking about in this and the other modules is subsurface drainage as opposed to surface drainage, where perforated drain lines are buried in the soil profile, typically 2.5 to 5 feet deep, designed to allow excess water when it develops in the soil to have a pathway to flow from the field to an outlet. Historically, clay or concrete tiles were used, and this is where the term tile drainage comes from. But almost all systems these days are designed using plastic perforated pipe. Taking a big picture view then of what we would like to see from a soil from an agronomic or crop production standpoint, what we'd like to have in that soil is that about half of the soil be the solid particles, primarily the mineral particles, sand, silts, and clays, and then a smaller percentage of those being the organic matter, maybe 1 to 8% of the soil. Although it's a small percentage of the soil, that organic matter plays an important role in how the soil is structured and functions, including how it is able to store water. The other half of the soil then is the void spaces or the openings in between those solid particles. These void spaces will then be made up of a mixture of air and water. From a crop production standpoint, we'd like to see about an equal percentage of both air and water in those void spaces, about a 50-50 split or about 25% air and 25% water relative to the overall soil volume. Almost all of the field crops need to be able to access oxygen from air in the root zone since they aren't able to get it from the atmosphere. Likewise, they need an adequate supply of water in the root zone to be able to support good crop growth and function. So there needs to be a good mix of both air and water in the soil, since an imbalance of too much of one and not enough of the other is going to put that crop under some stress, either from lack of aeration or lack of water, which will limit production and then limit yield. Taking a look now at water storage in the soil, we can break that out into some key water content levels that are levels of particular interest. So as we look at this figure, as we move from wetter at the top to drier at the bottom, the first water content level we can look at is saturation, or when all of the void spaces are filled with water. In a true field situation, we never get to full or 100% saturation because there's always some entrapped air contained in some of the smaller pore spaces in the soil. However, we still refer to what we call effective or field saturation because at this level the soil contains all the water that it's able to hold under those field conditions, and there's very little air and thus very little oxygen in the soil. So obviously this is not a good condition for crop growth because of lack of oxygen, and if it lasts for very long, we start to see some yield loss and potentially crop failure if it lasts much longer beyond that. It also obviously impacts field trafficability, and so it can delay field operations, which also can have an impact on yield. Following saturation then, when the rainfall or snowmelt event that caused that saturation stops, and assuming there isn't another large event right away, gravity will start to take over and drain water out of the larger pores in the soil. This drainage by gravity is called gravitational or free drainage. In poorly drained soils, however, there's often a restrictive layer or low permeability layer somewhere in the soil that limits this downward movement of water, which is the situation that we try and address through artificial subsurface drainage. Where natural drainage is adequate, though, gravitational drainage will continue until the larger pores are emptied, but water remains in the smaller pores. It remains in those smaller pores because it's held under tension forces working against those gravitational forces. The water molecules in the soil are attracted both to other water molecules and also to the surfaces of the soil particles, and in those smaller pores these tension forces are enough to hold that water against gravitational drainage. When that gravitational drainage stops, then we reach a condition we call field capacity. And again, water is drained out of the larger pores, but is being held in those smaller pores against the gravitational drainage. And so field capacity is the condition where the soil is holding the maximum amount of water that it can hold against that gravitational drainage. For most of our soils, then, field capacity ends up being about that condition where we've got an equal mix of air and water in the soil. And so field capacity is a desirable condition to be at as far as producing crops. Now, as we continue on, and assuming we don't get any intervening rainfall or irrigation events or something to refill that soil water, the crop will continue to use water out of the soil, and it will continue to do so all the way down until it reaches what we call the wilting point, or often called the permanent wilting point. And in this condition now, all the water that is left in the soil is just very, very thin films of water that are very tightly adhered to those soil particles. And in fact, they're held so tightly that the plants are just not able to exert enough suction to withdraw that water from the soil. And so hence, that's why we call it the wilting point, because at that point the crop is under so much stress that it wilts and dies. And this is a condition that's generally considered irretrievable, but that once we've gotten to that wilting point, the crop will no longer recover. So what we consider plant available water, or the water that's available for the plants to use, then, is that difference between field capacity and wilting point. But not all of that water is equally available, and so we can split that up into a couple of zones. One area that's readily available water, or water that plant can access without undue stress, and then beyond that we get into water that's technically available, but the plant is under some amount of stress trying to access that. The level of that split then is partly a function of plant type. Different plants are able to access water more easily than others, and then it's also somewhat a function of crop growth stage. But more or less about halfway between field capacity and wilting point is that level where we consider the difference between the water that's readily available or water that's available with some stress. Beyond that wilting point then is hygroscopic water, or again that water that's so tightly held that plants aren't able to draw it out, and the only way we can get that water out of the soil is actually through to drive it off through putting it in an oven or some other means beyond just natural withdrawal of water from the soil. And so then, as we look at how this relates to yield and why this is important then, as this figure shows, as we look at relative yield relative to soil water content, the better we are able to stay at or slightly under field capacity, the more likely we are to achieve that maximum yield, or at least not to reduce our yield because of water availability issues. And so as we move to the right beyond field capacity, then our yield starts to drop off because of lack of aeration. And that's the condition that we again are trying to address through subsurface drainage to take that excess water off so that it isn't a limitation on crop growth. And then as we move to the left, away from field capacity on the dry end, again we start to lose some yield, in this case now because of lack of water availability. One soil property then that's of interest then as we think about soil water is just the porosity of the soil. The porosity being the percentage of that soil that's those void spaces. So the total amount of water that soil could hold would then be equal to the porosity. But then only a portion of that overall porosity then is that water that will drain under gravitational or free drainage. And so that's then what we refer to as the drainable porosity, which is just a measure of the relative proportion of the overall porosity that's made up of those larger pores or those pores that will again drain under those gravitational forces. This drainable porosity then is a function of soil texture and soil structure. And so a table here showing the relative drainable porosity as a function of soil texture. And so sandy soils down at the bottom have a higher drainable porosity because the sand particles are larger particles, and so they tend to have larger void spaces or openings in between them. And so more of those pores will be available to drain under that gravitational drainage versus clay soil at the top where because of the smaller particle sizes, then then there's smaller void spaces in between those particles, and more of that water is held under those tension forces against gravitational drainage. Another soil property, and one that is particularly important as we get into drainage design, and especially when it comes to drain spacing then, is the hydraulic conductivity of the soil. Hydraulic conductivity is just a measure of the soil's ability to transmit water, or the ease with which water can move through that soil. Again, this is going to be a function of soil structure and soil texture. Basically, where we've got larger pore spaces and good alignment of those pore spaces, then water can more easily move through that soil and we'll have a higher hydraulic conductivity, versus at the other extreme, where if we've got a lot of small pores that aren't very well aligned, then that water has to take a very tortuous path to get through the soil, and so we have a very low hydraulic conductivity. Just showing a table here then of kind of the ranges of hydraulic conductivity and classes as defined by the NRCS. And so where we've got those higher hydraulic conductivities, when it comes to drain spacing, we can space our drains further apart because the water can more easily get to those drains, versus with the lower conductivities, we've got to put our drains closer together to get the same effect, because it's just more difficult for the water to flow towards those drains. And then as we lump several of the soil properties together that are important from a drainage aspect, we come up with what NRCS defines as the drainage class, which is just a reference to the frequency and duration of wet soil conditions and soil conditions that are such that they will hamper crop growth. And so we go from excessively drained or well-drained soils down to poorly drained or very poorly drained soils. The poorly drained soils obviously are ones that are going to benefit the most from artificial subsurface drainage, but by definition, even moderately well-drained soils are soils that often will have water levels in excess of what is desirable for crop production for some period during the crop growing season. And so where we develop those high water table or excess water conditions, particularly in the spring, to the extent we can lower that water table and get that excess water out of the soil, then we're going to encourage a healthier crop. So shown here on the left in the undrained condition, where we've got that high water table encroaching up into the root zone, those roots as they're developing will not penetrate below that water table, and so it will limit that root growth early on in the season. And then later in the summer, in July and August, once that water table's dropped, we've moved beyond the vegetative and root development stages, and so those roots will stay high and dry and just won't have a deep enough root zone to access water from, and so they'll be particularly prone to drought and disease and other stressors later on in the season. Compared to the condition then on the right, where we've lowered that water table in the spring, allowed those roots to develop over a larger root zone, and then later on in the summer then, as things dry out, we've now got a much deeper root zone and a healthier, more vigorous plant that's better able to deal with those conditions. And so again, that will then translate into improved yields. And so again, subsurface drainage is a way to deal with those high water table conditions when they develop. And so commonly we're putting those drains about 3 to 4 feet deep in the soil profile and allowing that excess water to drain out. So the water that will drain out is just that gravitational or free water, the water that's within that drainable porosity, the water from the largest pores. Water will remain in the smaller pores. We'll have a gradient drier towards the surface down to back to saturation at the tile elevation. And if we design it right, we want that water table drop to occur over a period of hours to days. And as a rule of thumb, most of our field crops will not tolerate excess water within a foot of the surface for longer than 24 hours and within 18 inches to 24 inches in the below the soil surface over 48 hours. And so that's typically what we try and design them for, is to get that water table at least a foot below the soil surface within a day and 2 feet or so below the soil surface within 2 days. The water content distribution following drainage will vary by soil type. And so we've got a soil here on the left where following drainage we've got a larger percentage of air-filled or empty pores versus water-filled pores above the water table. versus the soil on the right where less water is drained out of that soil, and so we've got a larger percentage of still water-filled pores versus fewer empty pores or air-filled pores. And so if you think as to which soil would be which, the soil on the left would be our coarser or sandier soil, versus the soil on the right would be a finer textured or more clayey soil. Again, because of the difference in the pore sizes between those soils, with the larger pore spaces in between those sandier particles, more of that water will drain out, a higher drainable porosity versus a lower drainable porosity in that finer textured soil. The water content distribution after drainage will also differ depending on the drain depth. And so on the left with the deeper drain, again, we'll drain more water out of the soil versus on the right where we've got a shallower drain closer to the soil surface, and so less water drains from that soil. And so this becomes a design trade-off and a design decision that we want to put those drains deep enough that we lower that water table, again, deep enough below the soil surface not to hinder crop production. But if we put them too deep, then we potentially cut off some upward flux of water from that water table later on in the season that can help feed that crop the water that it's looking for. And so we also don't want to go too shallow with the drains, because then we can worry about crushing the drains because of vehicle traffic. And so again, it becomes a design decision and a trade-off on depth when it comes to drains. When we get into drain spacing, we'll see that it's also a trade-off as far as the spacing that's required for those drains when we talk about pattern tiled or parallel drains. Now, as we look at how drainage actually works in the soil and how that water moves through the soil to the drains, when we put that drainage system in, when that drain system is operating in its design capacity, we've always got a free water surface or a little bit of air all the way through the drain lines into the field. And so we've got zero or gauge pressure or atmospheric pressure within the pipe. And then as the water table comes up and builds up above the drain lines, we create positive pressure outside the drains just from the weight of the water building up on top of itself. The same way as a scuba diver experiences more pressure the deeper he goes into the water, the higher that water table comes up above the drains, the more positive pressure we've got outside the drains. And so we'll start to get a pressure gradient developing as we move away from the drain. And so the gray dashed lines here then represent those lines of equal pressure emanating out from the drain. And then water will now flow following that pressure gradient from high pressure to low pressure or high potential to low potential. And those flow lines then will flow perpendicular to those lines of equal pressure. And so we can see that as we move away from the drains, the water is flowing down and then up into the drain. And so following those pressure gradients and flowing perpendicular to those equal pressure lines. We can see this if we look at a physical model of drainage. And so what we see here is a sandbox model where we've got a drain line in there, and we've built up a water table in that sand and actually above the surface of the sand, and then are injecting dye into that so we can trace those flow lines as that water moves towards the drain. We can also see here that because of just the nature of that model, that we've got an edge effect where that flow line, especially the one to the far left, is getting cut off because it can't flow below the bottom of the model. And so the blue line here then indicates where that flow path would like to go, but again, because of the bottom of the model there, it gets cut off and can't flow all that distance down. We can see the same thing out in the field because of the restrictive layer. And so that restrictive layer can play the same role in the soil where it can cut off those flow lines as they try and get to the drain. So that becomes another design constraint or guidance, is that we would like to keep those drains above the restrictive layer and as far above the restrictive layer as we can, again without getting too shallow, because as we put them closer to the restrictive layer, we cut off those flow lines. It's just more difficult for that water to be able to flow into the drains. And especially if we put them in the restrictive layer or below the restrictive layer, now we limit the ability of that water to get to the drains. You can also see that it looks somewhat counterintuitive that the water is flowing uphill or up into the drains, and so actually most of the water that flows into those drains will flow in from the bottom, and the only water that flows in from the top is the water more or less directly over the drain. But again, as we think back to that last slide, it's flowing down those pressure gradients or down those potential gradients. And so that was some basics of soils and how drainage works. Now as we move into basic drainage design concepts, as we look at objectives for that drainage design, some obvious objectives that we may want to look at are, first of all, obviously providing for the needs of the crop. That we're trying to design that system to improve crop yield and the consistency of our crop yield. We also want to provide for the needs of the soil, and then also providing for trafficability of that soil. We want to design that system so that it functions with hydraulic efficiency and that also uniformity. So the more uniform we can get drainage across the field, again, the more consistent our yields will be. We'd also like to design that system to be as maintenance free as possible so that we prevent it from silting up or filling up with sediment. And so that system, that plastic pipe, once it's in the ground, can last for many, many years. And so the extent we design that to be maintenance free, we'll have a system that works well for a number of years and potentially for generations. We also want to try and design that system to minimize any unwanted impacts, both environmental effects of water quality, also impacts on downstream neighbors as far as flow. And one of the reasons we're in this training then is we also want to the extent possible, design that system for drainage water management, assuming the topography will work for that. And so, assuming that topography is conducive to drainage water management, if we take that into account as we're designing the system, it's much easier to design a system for drainage water management, whereas if we have to go back and retrofit it later because we didn't think about that at the time of the design, that can often be more difficult to try and retrofit drainage water management onto an existing system. Now, looking at factors that go into our drainage design, there's going to be some of those factors that we just have little or no control over, and so in essence these become constraints on the system. And some of those factors are going to be the climate, that we're more or less stuck with the climate that we're in. Likewise with soils, we can't really do much about the soils that we've got, so we got to work with the soils that we have. With topography, again, we can make some minor changes to topography, but more or less have to work with our topography. Outlet is a huge consideration. We need to know that we can access an adequate outlet. So if we don't have a place where we can take that water, that's going to limit our ability to work with artificial drainage. And then also is the legal or regulatory framework. And so, again, we need to understand the legal and regulatory framework at the location that we're at, whether that's it's going to be some combination of local, state, and federal regulations that all may come into play when it comes to drainage. And so we need to be aware of those and work within those constraints. The other factors then are the ones that we do have control over, and so these become our design choices. And so as we look at those, we can look at what areas do we want to drain or what areas need to be drained. So for some fields that may be the entire field needs drainage, and so we're going to look at a pattern tiled or a regular tiled field. In other fields it may just be portions of the field that need some additional drainage, and so in those types of situations we may be just looking at a targeted drainage system where it may just be a few lines here and there to try and address some problem areas, potentially building off some laterals into some areas, but not across the entire field. The drainage rate or drainage coefficient, which is just a measure of the design capacity of the system, is going to be one of the key decisions we make, and we'll talk more about what that is. Drain sizes, we certainly can choose what size pipe we're going to use, what grade we're going to put those pipes on, the materials we're going to use. Again, most often that's perforated plastic pipe, but we can still make choices between single wall corrugated pipe, dual wall pipe, regular perforations, narrow slot perforations, sock, and so there's a number of decisions related to materials. Layout is a big consideration, and so working with layout to try and achieve uniformity of that drainage system will be a key consideration. And then the outlet configuration. Again, assuming we've got an adequate outlet that we can use, can we get to that outlet just via gravity flow? If not, can we otherwise develop an outlet so that we can get there via gravity? Or if we've got an outlet but there's just no way we can get there via gravity, then we've got to look at a lift station or pumped outlet. As we look at the steps that go into drainage design, this is one way to visualize it in the context of a flow chart. And so we start with the first step is just collecting background information that's going to go into that design, just information on soils, topography, crops that we're going to grow, climate, things like that. And then the next step then is to look at, is drainage in fact needed? So making sure that the drainage conditions or the drainage concerns are happening frequently enough that artificial drainage is indeed needed, or the best way to try and address those versus something that just is happening rarely or infrequently where that drainage investment may not be a wise one. So assuming that we answer that yes, then we move on to, again, key concern, making sure that we've got an adequate outlet. So we need to confirm that we've got a place that we can take that water and that that outlet is adequate to handle the drainage water that we're planning to deliver to it. So if we can't answer that yes, then we're more or less stuck at that point. But if we can answer that yes, then we move on to selecting a drainage coefficient, which means selecting drain spacing and drain depth. And when we're talking about drainage coefficient, that's just a measure of that system capacity again. Then we move on to laying out the system. And then once we've got that layout, then we work with our topography to figure out what our drain grades and depths are to match that topography. And then we can move on to actually sizing the drain pipes. And then pulling all that together to be able to actually go out and install that system. This flow chart shows that as a linear process, but as we move through drainage design, often what happens is we make one decision that then causes us to go back and revisit some earlier decisions, and so typically this ends up being an iterative or somewhat circular process as opposed to a purely linear process. Now, assuming we've answered yes to those questions on whether drainage is needed and confirming that we've got an outlet, again, the first step beyond that is selecting the drainage coefficient and drain spacing and drain depth. And that drain spacing and drain depth come together to combine with the properties of the soil to determine that drainage coefficient, which again is a measure of the overall capacity of that system or the design capacity of the system. And that drainage coefficient we express as a depth of water as measured over the soil surface that we remove within a 24-hour or 1-day period. Again, because the drainable porosity is going to vary depending on different soil types, the actual depth that the water table will move in the soil will vary, but if we express it as a depth above the soil surface over that overall drained area, then it becomes a consistent way to look at that design capacity. And it's the combination of depth and spacing along with the properties of the soil that determine that drainage coefficient. And so the farther we space those drains apart, the farther water has to go in between those drains to be able to get to the drains. The deeper we put those drains, then the more driving pressure we've got as the water table comes up to drive that water towards the drains. And so it's the combination of depth and spacing along with soils that determine that drainage coefficient. As we look at the effect of drain spacing, then again, we're trying to lower that water table within 24 hours to get it a foot below the soil surface and 2 feet below the soil surface within 48 hours. So the water table will start to draw down. Initially, the water draining more quickly as closer to the drain. The highest point in the water table will then be midway between the drains. And so if we put the drains closer, that drop happens more quickly, just again because less distance that water has to travel from the midway point between the drains to get to the drain and flow out. Now looking at how drain depth and drain spacing all relate together to get to drainage coefficient. It will depend on the soil type, but we can come up with for a soil type, if we know the soil properties, any combination of drain depth and drain spacing to get a desired drainage coefficient. So if we look here at the curve for a drainage coefficient of 1/4 inch per day, we can see that, again, we can come up with an infinite number of drain depth and drain spacing combinations along that curve to come up with that 1/4 inch drainage coefficient. Same as we look at these other curves for different drainage coefficients. Again, any number of combinations of drain depth and drain spacing to equal that drainage coefficient. The other thing you can see here then is if you look at a common depth, as we put the drains closer together, we move up in drainage coefficient. And then also if we look at a consistent spacing, as we put the drains deeper, that drainage coefficient goes up. And so we can work with drain depth, drain spacing to come up with a desired drainage coefficient to match what our system goals are. Again, this is also a function of the soil, and so these curves would be for one particular soil type. For a different soil type, we'd have to develop a different set of curves for particular to that soil type. If we look at what is the correct drain spacing, then again, we want to get those spaced such that we get the water table out of the top part of the root zone in a timely fashion. But if we space those drains too far apart, as shown in the bottom part of the figure, we just don't get that water table drop quickly enough in between the drains, and so we start to see that impact on crop growth and yield in between the drains. And so we want to get them close enough to get that desired water table drop, but we don't want to put them too close that we're not getting adequate return on that investment from putting the drains closer together than what we need to get that desired water table drop. And so one of the things we can do as drainage researchers is look at modeling the crop response to that drainage investment. So here's some example data from Waseca, Minnesota, using 85 years of climate data from the Waseca area. And we can look at, for some different soil types here, what the response of the crop is to that drainage. And one of the things we typically see with drainage then is what we see here, where there's a relatively sharp increase going from very little drainage to providing some drainage to the crop. But as we increase that drainage coefficient more and more, we see less and less incremental benefit because of that additional drainage investment. And so if we had perfect information, then we could use that to optimize that drainage decision. But in most cases, we don't have that luxury. And so we tend to fall back on guidelines for those drainage coefficients. And so what's shown here is some guidelines for that drainage coefficient that come from American Society of Agricultural and Biological Engineers standard, given here for mineral soils. For typical field crops then, that recommended drainage coefficient ranges from 3/8 of an inch to 1/2 an inch. For higher value or truck crops then, we can justify a higher drainage coefficient. Also shows that where we've got surface inlets on the system, we need to size up that drainage coefficient because that system now needs to be able to handle both the subsurface water but also the additional surface water that we're designing that system to handle, and so that drainage coefficient needs to go up to reflect that. Also then shown as organic or peat or muck type soils, we need to look at higher drainage coefficients for those types of soils versus the typical mineral soils. You should note that these drainage coefficient guidelines were developed for the humid regions of the U.S., and so as we move further west into the dry subhumid regions of the western Corn Belt, we may be able to get by with lower drainage coefficients than what's shown here. Once we've chosen the drainage coefficient then that we're going to design the system for, we need to figure out for a pattern tiled system what the drain spacing we need to use then to get that drainage coefficient given the depth that we're going to put those drains at. And so the equation that's typically used for that is a steady state drain spacing equation that was developed by Hooghout from the Netherlands in 1940. Not so important what the actual equation is, but just to recognize that that equation takes into account properties of the soil as well as properties of the water or the design, that as that water table comes up, what that driving force is to move water towards those drains. That Hooghout equation is not always the most convenient equation to work with, and so in many of the Corn Belt states, the state NRCS or another entity developed a drainage guide then where they applied that equation to typical soils in that state. And so you could look up using a table just your soil type, and then based on the depth that you were going to put your drains at and the drainage coefficient, come up with a recommended drain spacing. And so for example here, for a soil from the Minnesota drainage guide, given two different depth choices, either 3 feet or 4 feet, then looking over to your drainage coefficient, you can come up with a recommended spacing. However, some states don't have a drainage guide that's available, or if they do have a drainage guide, that drainage guide may be not maintained or out of date. And so one of the things that we've developed here at SDSU is an online drain spacing calculator, where by entering the desired drainage coefficient, some soils and system properties, you can calculate a desired or the recommended drain spacing. It's also then a way that if you want to look at drain depth and spacing combinations different than what are in those drainage guides, that you can play around with a variety of different depth spacings and drainage coefficient combinations. Looking at an example problem here then of drain spacing, which would be something typical where we've got more than one soil type in the field and where those two different soil types have different drain spacing recommendations. And so I'll pause here for a moment, and I'd encourage you to go ahead and hit pause on the recording and take a minute to think about these two questions. So the first question being, what drain spacing would you use if these soils and their spacing recommendations are shown below? And then the second one, what factors would support the use of a narrower drain spacing? So hopefully you've taken a minute to think through this and pause to do that. But if we look through what some of the options would be for this type of situation, one option would be to do the whole system at 83 or 80 foot spacing if we use round numbers across the whole field. If we do that, then we'll have the desired drainage that we're after in soil 1, but in that area of soil 2 then, because we've got wider spacing than what's recommended for that soil, we'll have will be under-drained or have a little less drainage in that part of the field than what we would like. And so we won't have uniform drainage and we'll have less drainage than what we would like in that area of soil too. Of course, we could do the other end and do the entire field at 40-foot spacing. In that condition, now we've got adequate drainage, or the drainage that we desire in soil 2, but because it's less than the spacing recommendation for soil 1, now likely what we're doing is spending more money on or investing more money in soil 1 than what we're going to yield return from that drainage investment. And so that's probably not going to be an ideal solution there. We could split the difference and do something like a 60-foot spacing across the whole field. And so if we do that, then we'll be a little under drained in soil 2 and a little over drained in soil 1. And so again, that may not be desirable. But there's nothing that says that we have to use the same spacing across the whole field. So one option would be to do the whole field at 80-foot spacing, and then in those areas of soil 2 come back in and put lines halfway in between those at that 40-foot spacing. And so now by changing that layout and working with the spacing and the different soil types, we get the drainage that we're after, and more uniform drainage across the whole field for those different soils. And thinking about that second question, factors that might support the use of a narrower drain spacing, one would be higher value crops, because we would expect a higher return from that narrower drain spacing. Another potential situation might be where it's in a low area and we're expecting some additional surface water that drains down in that area that we need to account for. So looking at kind of a summary of drainage coefficient and spacing, we generally don't have enough data to really know what the best drainage coefficient is for our soil, crop, and region. And so again, experience and long-term observations or guidelines are important, but it all boils down to risk management for the farmer. Are we trying to protect the crop for any condition, for more of an average condition, or something more or less than that? So again, it comes back to risk and how risk averse the producer is and how much money they're willing to invest to compensate for that risk. It is an area of ongoing work in drainage research to try and develop new and improved recommendations. Now looking at drain depth, we would like to be able to design that so that depth is as uniform as possible across the field. And so that's going to depend on system layout. It's also going to depend on topography. And so on flat and rolling topography, keeping that consistent depth becomes more difficult. So one extreme here, looking at a tabletop flat field, 1,000 feet run. If we start at a 3-foot depth and use a relatively shallow grade of 0.1%, over the 1,000 feet, then we're going to drop a foot with our tile grade, and so we'll be 4 feet below the surface. And so that difference in depth then is going to result in a difference in drainage coefficient. And so if this is that set of drainage coefficient curves relative to depth and spacing, by changing from that 3-foot depth to the 4-foot depth, we're going from here a drainage coefficient of 1/4 inch per day to a drainage coefficient of 3/8 inch per day. And so just that change in depth across the length of that run then results in a change in drainage coefficient, which means that we don't have uniform drainage across the field. Another consideration of depth then is making sure that we've got adequate depth to make sure that we don't crush the pipes from vehicle traffic. And so from another ASABE standard, recommendations for a well-bedded drain, a minimum of 2 feet of cover being from the top of the pipe here. For more of the lateral size, 3, 4, 5, and 6 inch pipes, and 2.5 feet of minimum cover for larger size or main size pipes. Those numbers are for mineral soils. Organic soils are going to require more cover than that, and so one reference for that would be Conservation Practice Standard 606, which has some recommendations for those organic soils. Now looking at layout as our next step. Layout is going to be one of the most important steps, assuming again that we've got an adequate outlet. And layout is generally a mixture of art and science, and so it's often where the real brains are needed. And that layout is going to determine how uniform that drainage is. Layout is working with the topography of the field to try and get as consistent a depth throughout the field as we can. And so again, looking at a challenging condition of a flat field, in this case 2,000 feet long, if we run those laterals the full distance of the field, and even working at shallow grades, 10th percent being something that would commonly be considered the shallowest that we may want to go with a pull type or farmer grade plow. Contractor grade plows may be able to get by with going a little shallower, but even then we'll still see a significant difference in pipe elevation just because of that grade that we've got to maintain on the pipe and not having grade in the field. And so 2-foot difference or 1.6 foot of difference depending on the grade that we use there. And so one way to try and minimize that difference in depth, which then means a difference in drainage coefficient, is to work with layout. And so one option would be to split that field in half, put in a sub-collector or a sub-main, and so now our laterals are running half the distance, which then splits the feet of fall in half, and we'll have a little more uniform drainage coefficient, but the trade-off is going to be more connections and more feet of main. Now looking at another example where we've got a natural field grade of 0.1%, this would be more or less kind of an ideal situation where we can match the grade of the pipe to the natural grade of the field. And so in a condition like this, now it's easy to keep those laterals at uniform depth, still maintain the grade that we need, and get consistent drainage across the field. Looking at some guidelines for layout, first of all, one is that we want to start with a good topographic survey of the entire field. That's the only way to look at the entire field at once and to make sure that drainage system is going to operate as a complete system, that water is going to flow, and things are going to connect and drain the way that we want them to. Some other recommendations then are to put our mains or sub-mains on the steeper grades, and then align the laterals more along the contours, offsetting them enough to make sure that we maintain grade. That has a couple of benefits. By putting those mains on the steeper grades, we can get by with a little smaller size pipe because of the steeper grade. And then also by putting those laterals more along the contours, those laterals then act more as interceptors as that water moves down slope, and so we get a little more efficient system with those laterals acting as interceptors. Now here we've got another example problem for you to think about, but we've got a field here 800 feet by 1,000 feet, although a little odd shaped. On the right hand side, our outlet down there at the bottom right, the contours as shown here. The idea here for you to think about how you would sketch out or lay out a drainage system for this field. But first of all, just a kind of a quick review of working with contour maps. We've got a feature here where we've got contours that are pointing down the hill, and so that would be a ridge running across the field. And we've got an area here of contours where the contours are pointing up the hill. Not quite as defined as that ridge, but this would be a little bit of a draw then where those contours point up the hill. And there's an area here on the left where the contour lines are close together. And so of course that's a steeper area versus this area on the right hand side where the contour lines are spread further apart is a flatter area. And so Again, I'll pause here for a few seconds and encourage you to hit pause and take a minute to think about how you might lay out a system. Where would you put the mains and where would you put the laterals for a layout for this field? And so again, hopefully you've taken a minute to think about some potential layouts, but let's discuss a few different options. One option would be to have our main run along the bottom edge of the field and then having the laterals run up and down, or assuming north is up, then we've got laterals running north-south. Some things to think about with that layout. One is it's a nice rectangular layout, so it would be easy to design and install. Our laterals are going to be relatively aligned with the contours, and so again, that's often desirable. We will be having to plow through that ridge, and so depending on the height of that ridge and our equipment, that may be a concern that we would have to think about. Another option would be to have a main running along the right-hand side or the east side of the field, and then have our laterals running east-west. In this case now our laterals are running primarily up and down the slope, and so we may have to use a little larger main because it will be on a shallower grade than if we had the main running along the bottom. But we know getting grade on the lateral shouldn't be a problem since we're running up the slopes. But as we move into design for drainage water management, one of the things we'll see is having those laterals running up and down the slopes will make drainage water management more difficult. Another common option would be to have a main that runs more or less following that draw. So that allows us to take advantage of the topography and have a little more freedom on lining those laterals up more or less lined up with the contours. But the drawback there is going to be that we'll have more connections, that we've got laterals coming off on both sides, and so it'll be a little more difficult system to install. Those are just three options. With any drainage design, there's always multiple options for layout. All will have their unique advantages and disadvantages. Now looking at drain grades and depths. What we're trying to do again with drainage system design is match those field grades with the desired drain grades, and so we get a system that works well and is economical. Some considerations with tile grades: we need enough grade that we keep the water moving and that we keep any sediment in the water suspended in that water so it flows out of the system. Flat grades are going to be more prone to sediment buildup. We're also going to have a smaller margin for installation error, and so those installation errors are going to be more costly. Steep grades are going to result in higher velocities of water in the pipe, and so the good thing is that increases the tile capacity, and so we can get by with smaller size pipe to carry the same amount of water. But if we get too steep, we can get very high velocities and potentially cause tile failure by suck holes, where we get negative pressure that pulls soil into the tile line. We need to watch out for steep to flat grade changes, and so where that grade changes by an order of magnitude, say going from 1% slope to 0.1% slope, or 2% slope to 0.2% slope, where we get those types of grade changes, now we're creating high pressure, where that high velocity water goes to flatter grade and becomes low velocity water, and we get a pressure increase, and so that can create blowouts. We need to pay attention to minimum grades, again, to make sure that we got enough water velocity to keep that sediment suspended. And so again, refer you to Conservation Practice Standard 606 for velocity requirements. Some standard guidelines then here for drainage systems, depending on whether those drains are going to be subject to fine sands or silt entering the pipe. where we've got enough clay in the soil, 30% or more clay, those soils tend to be more stable, and so we're not as worried about sands or silts entering the drain system, and so we can get by with shallower grades versus those where we've got a higher percentage of those silt and fine sand particles in the soil, and so there we are concerned about them entering the pipe and becoming a siltation hazard. And so unless we deal with that some other way, either through narrow slot pipe or sock or something like that, we need to provide a steeper grade to make sure that we keep those in suspension and flowing out of the system. Just to clarify here, the tile there refers to clay or concrete tile, the tubing there refers to plastic drain pipe. And then just a reminder of the difference between fall and grade. We need to know both the fall and then the distance that occurs over, and then we can calculate grade. Or if we know the grade and then the distance, we can calculate fall. And then the last step we'll cover here is drain sizing. So there are three things that are going to determine the flow capacity of a drain pipe. One is the grade that it's on. Another is the material. So differences in material are going to affect the friction or the resistance to flow. And then the third is the pipe size. So the grade we get from our layout. The material is what we choose, and then what we're after is what size pipe we need. The flow that pipe needs to be able to handle then is going to be a function of the drainage coefficient, which is the design decision that we've made on the capacity of the system. And then the area that pipe is going to drain, which for a parallel or pattern tiled system is going to be the drain spacing times the length of the drain. And so we can calculate then the flow as the drainage coefficient times that area, making the necessary unit conversions to keep it in consistent units. And so once we know the area, the drainage coefficient, the drain grade, and the material, we can size the drain pipe necessary to handle that flow. So it's all based off of Manning's equation, but typically we would use a tool to solve that. And so that may be charts and tables, for instance, out of NRCS Engineering Field Handbook, Part 650, Chapter 14. That may be a calculator slide chart from one of the pipe manufacturers, or that may be an online calculator. And so that leads us now into some of the tools and resources that are available to assist with drainage design. And so one of those, again, is the slide calculators that are available from the major pipe manufacturers that are a convenient way to be able to size drain pipes. Some NRCS references then related to drainage design are Part 650, Chapter 14 of the Engineering Field Handbook related to water management and drainage. Part 624, Section 16 of the National Engineering Handbook on Drainage of Agricultural Land. Conservation Practice Standard 606 that we referred to a few times already. State drainage guides or other resources, and so a table here by state of drainage resources used by those individual states, and so shown here Illinois, Indiana, Iowa, Michigan, and Minnesota. And now for Missouri, North Dakota, Ohio, South Dakota, and Wisconsin. The University of Minnesota Extension Agricultural Drainage website, maintained by Dr. Gary Sands, has a great collection of fact sheets, other publications, drainage calculators, and a variety of other information related to agricultural drainage. And the online Illinois Drainage Guide, in addition to providing drainage recommendations for Illinois soils, contains a wealth of information general to subsurface drainage design and drainage design in general that makes it a great resource. And then the previously mentioned SDSU Drain Spacing Calculator, which provides a tool for developing drain spacing recommendations, particularly in areas that don't have a drainage guide available. And so with that will conclude this distance learning module. Hopefully was worthwhile to you. Those who aren't familiar with drainage, hopefully you got a good introduction and background on drainage concepts. For those of you that do have some experience with drainage, hopefully it was a good refresher. And so with that, I thank you.